This is the practice number 4 and it's named Solid or Casing Cementation, Quench and Temper, and you are the team number 5.
In this practice, we must to apply the principles of solid-state diffusion to cement carbon for increase the mechanical properties in the surface. Then we must to analyze the effect of cementation variables on the results obtained.
For this practice, we used a 4140 steel. For the cementation, we use a safety equipment for high temperatures. Also, we need an iron box with lid that was closed with bentonite, and inside it was a mix of charcoal, sodium, barium, and calcium carbonate, and twisters for the iron box and muffler. And after, we used all the metallographic materials and the beaker zerometer.
First, we cut the 3 pieces of steel into slices, about 1 centimeter of thickness. Then we crushed 170 grams of coal, also 5 grams of sodium carbonate, 21 grams of barium carbonate, and 6.5 grams of calcium carbonate. Then we put a lower bed of cementation material in the base of the box and introduce the samples, leaving enough space between them and covering completely with the cementation mixture. Then we seal the lid of the box with clay and we leave the box with the piston side in the muffle with a temperature of 900 Celsius degrees approximately for 12 hours. Then we take out 1 piece and quench it, and the other 2 pieces we heat it to 800 degrees for 15 minutes. And then we took out 1 piece and quench it in water, and the piece that remained in the box was heated to 200 degrees for another 15 minutes. After this, we do the metallographic process and determine the beaker hardness in the 3 pieces, and we determine the change in microstructure and grain size. Well, this was the procedure that we understood and that we did in the laboratory. But the procedure that it was supposed to be was that after the 12 hours of 900 degrees, we needed to quench the 3 pieces and then reheat 2 of them to 800 degrees for 15 minutes, then quench the 2 pieces and 1 of them reheat it for another 15 minutes into 200 Celsius degrees.
These are the phases we had the way we conducted the practice. The first step was to austenitize at 900 degrees, and we can see from the diagram that at 40% we form a uniform austenite microstructure at 900 degrees. Then one of the pieces was quenched to room temperature, therefore producing a uniform martensite microstructure, while the other 2 were placed in the oven at 800 degrees. Again, on this diagram, we can see that at 800 degrees, we are still in the austenite zone. Therefore, the austenite microstructure is maintained. After this, one of the pieces was quenched to room temperature, producing a martensite microstructure. The last piece was placed in an oven at 200 degrees. This creates this curve, this cooling curve. It's a very slow cooling curve from 800 to 200 degrees, and then from 200 to room temperature, producing a perlite phase. These 2 tables summarize the different phases for the 3 pieces in both the ideal way this practice was supposed to be done and the way we did it. As we can see that the first part was to heat to 900 degrees, where we always have an austenite. Then in the ideal way, the pieces were quenched to room temperature, leaving a martensite. Then 2 of them were heated again to 800 degrees, making austenite again. They were both quenched to room temperature, leaving martensite. And finally, the last piece was tempered at 200 degrees, creating a tempered martensite phase. The difference between phases and microconstituents is that a microconstituent is a phase or a combination of phases which are identifiable within a microscope. In our practice, the microconstituents are, we have the primary one, which, as we can see from our composition at the reaction, is 49.45%, while the eutectoic microconstituent perlite is 50.55%.
In the sample that was quenched after 900 degrees, we do the Vickers hardness test, starting from the outer side and going deeper into the center of the piece. We observed a average hardness of 631. In the microscope, we observed the sample and we could see that the grains grow in flat, narrow plates. This means that it is martensite phase, and we could prove this because the hardness is very large. Grain size is of 10 ASTM. A larger grain size means larger hardness and better mechanical properties. In the piece that was heated to 800 degrees and then quenched, we obtained a Vickers hardness of an average 413. We could see in this graph that the hardness didn't change as the distance from the edge changed, and the grain size was of 9 ASTM. We could see that here we don't have all martensite. The hardness is not too high, and the grains are not in these flat, narrow plates. This could happen because the piece was heated to 900 degrees and was left in the environment temperature like 30 minutes until the muffle reached the 800 degrees. Then the piece was introduced to the muffle, but just for 15 minutes. This could make that the piece didn't reach this temperature and it didn't reach the austenite phase complete. So we could have a mix of different phases that at the end didn't convert all in martensite. And in the piece that was heated to 200 degrees, we see a similar hardness of an average of 429 and the same grain size, and we observe the same pattern that the Vickers hardness stayed the same as the distance from the edge increased. The conversion process was supposed to decrease the hardness as the distance from the edge increased, but in our practice we didn't notice this pattern. This could maybe happen because all the part that we analyzed was the outer surface. We could prove this because the average hardness was of 429, and on books we found that the hardness of the same steel is lower, it's of 300. So we could see that all of our Vickers tests were made in the outer surface where there were more carbon.
In order to understand better the practice, we must to analyze some concepts. For example, carburizing is a thermochemical process in which carbon is diffusion and the carbon atoms throw for the surface that are in contact with the carbon. Carbon equivalent is an empirical value in weight percentage relating to combined effects, different alloying elements used to making of carbon steel. Carbon potential is a measure to the capability of furnace atmosphere to impart carbon into steel during heat treatment. The carbon potential of atmosphere is defined as the carbon content in a thin sheet of pure iron, and they are in equilibrium with the atmosphere. And the surface that is changed in the carburizing process is the cemented layer. It's the zone that are affected after the process and has a greater carbon content. The hard cover is the surface area that after the heat treatment has an upper hardness like 58 or 60 in Rockwell, and the carbon percentage is upper to 0.5 to 0.8 percentage of carbon. Quench is a rapid way to cool a material in a determined temperature after a heat treatment. Is used to increase the hardness of the steel. Chamber is a heat treatment for control the final properties of the steel and change its toughness. The diffusion is when the carbon atoms drop in the kiln I'm going to the steel surface and add in this the carbon content increase in this part.
There is three types of cementation. The first one is a solid cementation that use a steel box that contain some mixed with some substances rich in carbon. With this method, the occurrence layer varies from 0.3 millimeters to 2 millimeters, but this process is very slowly. The gas cementation is the more efficient process, and because it has a major control of penetration, the surface is homogeneous, and the liquid cementation use molten salts rich in carbon too, and it also is a quickly process and an exact process. In gas cementation and liquid cementation, you can do big number of pieces simultaneously. The application of this method is in order to color the surface of a piece without making modification in the core. You want that the core of the steel have low carbon, and that makes that the resistance to the fatigue is good, and also is tenacious. Steel in the surface has more concentration of carbon, and with that the resistance to wear is higher and deformations are lower. The surface is harder with this concentration of carbon. This treatment is good for pieces that must be resistant to shock and tenacity together. For example, pinions and axes and some cementation could only be applied for steels that have less than 0.2% of carbon. These steels have the characteristics of being soft and weak, but also outstands the ductility and toughness. A plus, or in addition, these materials are not expensive to produce.
There are many types of furnace. Depending on the field, can be natural gas furnace, cold furnace, and endogas or exogas furnace. And depending on the process, can be continuous pressure type furnace with ceramic roller hard transportation system, rotary drum type continuous carburizing furnace, PT type top loading furnace, and mesh belt type bright carbonizing furnace. Want to find the distance of diffusion? So at 938 Celsius degrees, iron has a FCC structure. So the activation energy is 32,900 calories per mole, and the initial diffusion is 0.23. So according to the formula of the diffusion, we have that the diffusion is 2.42 times 10 to the minus 7 centimeters by second. According to the fixed second law, the distance is going to be 0.019 centimeters.
Some cemented steel frame machinery that are the most common steels. We have the 1018 that is used for pinions, endless screws, spikes of the action, and also we have this 5015 that is used for some pieces that are restricted resistance in the core, but with good fatigue resistance. 8620 that is used when you need a good fatigue resistance, and also is used for pinions, where boxes of trucks, cars, and agricultural machines.
In this practice, I learned how tempering heat treatment should be done, and how a heat treatment can change the properties in the steel's life.
Throughout this practice, I learned the process of carburization and the different steps that need to be taken in order to do this process. I also learned how, according to the different heat treatments, the mechanical properties of the steels will change.
With this practice, I learned that it is very important to do the quench, because the results are very different when you do quench between each treatment and when you don't make.
In this practice, I can learn about the carburizing process, and we did the different samples with different temperatures, and we can see that the hardness changes in factor of the temperature change.
In this practice, I learned the importance of understanding the procedure, because this changes a lot the results. I learned the different phases that are formed in the different temperatures, and these phases lead to different mechanical properties.